All right, hello y'all. We're welcome to my DB chemistry curriculum. Today we're doing lesson 68, reactivity 1.2.1. We're going to talk about bond breaking and bond forming, how it absorbs and releases energy respectively. So we're going to calculate the enthalpy change of reaction given average bond enthalpy data. So with that said, we can just start by talking about what happens when bonds break and form. You can kind of think of bonds a little bit like magnets. When you apply enough energy, you can pull them apart to break apart. Now, because of this, we can say that bond breaking is going to be endothermic. But also, like magnets, if they come together, so if you have a magnet here and a magnet here, and they come together, they usually crash with a loud noise. You can think of that as like the release of energy, because it is. And therefore, bond forming, on the other hand, will be exothermic. So bond breaking is endothermic. We have to apply energy to pull them apart. And bond forming is exothermic, like magnets colliding. In addition, when we start thinking a little bit about this energy, we actually call this bond enthalpy. Specifically, bond enthalpy referring to the energy required to break 1 mole, it's always going to be 1 mole of always gaseous chemical bonds. So we're always referring to 1 mole of gaseous bonds. The reason we use gas instead of liquid or solid is because if it's in the liquid and solid state, it will already take extra energy as those states start from lower energy. Furthermore, we have to keep in mind that when we are forming or when we are doing a reaction, we just have our quick graph without any of the axes, and this would be an endothermic as it increases. Our products are going to be less stable as they have higher energy overall. Meanwhile, let's keep in mind that for an exothermic reaction, our products will be more stable. So, with all this in mind, let's actually look at the energies of chemical reactions taken from the idea of bond enthalpies. So, actually, before we do, one last thing about bond enthalpy values. These values are in section 12. And the key thing about that is that these are always average values. These are average values. Now, the reason for that is if we look at different molecules like methane, which is CH4, that carbon-hydrogen bond is going to act a little bit differently than if we had C11O single bond H. These will be different bonds. This is not the same as this, as we have a much more electronegative element pulling the electrons over towards the oxygen. Meanwhile, this right here is a completely non-polar molecule. And so, because these exist in different states, we actually just average the values of these bonds, and that's how we get our bond enthalpy values. So it's really important to note that these are not exact, and therefore your chemical reactions that you form, or sorry, these chemical reactions that you calculate values for, will not be accurate. They will get you in the ballpark and generally tell you whether something's endo or exothermic, but they will not be as precise as the actual enthalpy of the equation. But with that said, now we can start calculating enthalpies. Enthalpies of chemical reactions, or from bonds in reactions. So when we have a chemical reaction, like for instance, the formation of HF through hydrogen plus fluorine to react to form two hydrofluoric acid or HF, whatever. When we have this reaction, what we have to do is we have to break these bonds. And then we have to form this bond. And if we're breaking a bond, that means energy has to be applied. And then if we're forming a bond, we get that energy back out. We can look at these changes in energy. We can look at the delta H or the change in enthalpy by looking at the enthalpy of reactants and the enthalpy of products. So we're going to go back to our graph here. If our products have a higher enthalpy, then we know that this is endothermic and that our change, our delta H, should be positive. If our products have lower energy, then this will be exothermic and our delta H will be negative. So from this, we can figure that if we need a negative value for something that releases energy and a positive value for something that has to gain energy, we can derive that our equation for delta H is going to be the sum of the enthalpy or bond enthalpy of reactants minus the sum of the enthalpy or bond enthalpy of products. So if our products have less energy, by subtracting these, we will get energy out of it. So with this said, let's go ahead and try a reaction. Let's start with the one that we actually just did the example for. So we'll look at the, oops, let's do example. H2 plus F2 reacts to form 2HF. So what we have to do is analyze the bonds in each of these. H2 is a single bond, F2 is a single bond. When we add these together, we react to get 2HF. Or, if we want to look at it a little different way, we have HF and HF. So we have these two molecules. We can look up these values in section 12 of our data booklet. But what I'm going to actually do is try and set up our equation first. So I will do the sum of the H bonds plus the F bonds minus 2 times the HF bond. Here is my setup for my reaction. When I look up these values, I find that I have for hydrogen bond, 436 kilojoules mole inverse. I add that to 159 kilojoules mole inverse. And I subtract by 2 times 567 kilojoules mole inverse. I keep doing kilojoules per mole inverse because this is a bond enthalpy value, which we define as the energy required to break 1 mole. And we display it in kilojoules, otherwise this answer would be completely unmanageable. When I plug this into my calculator, I find that delta H is equal to negative 539 kilojoules mole inverse. So I know that this is going to be an exothermic reaction, releasing quite a bit of energy. We're going to do one more example before we end it here. You should try this one out on your own, but it might be a little difficult as I'm writing it in more of an organic chemistry format. So I have ethene plus hydrochloric acid reacts to form chloroethane, CH3CH2Cl. The reason I have this one is it shows us a little trick we can often do when calculating energy from reactions with bond enthalpies. But try and pause it, see if you can figure it out on your own, and then come back for the answer. Starting now. In my reactant side, I have a carbon-hydrogen bond, but I have four of them. And then I'm going to add that to one hydrogen chlorine bond. On my react or product side, I have the same carbon hydrogen bond, but I have five of them. And then I have one not hydrogen, carbon chlorine bond. So very quickly, how did I figure out what bonds are present? Well, when writing a formula for an organic compound, often we just write the individual groups, it's CH2, not CH3, CH2. Then we have a double bond, and then CH2. HCl is as follows, and those react to make CH3, which once again, it's written as the bonds. Single bond, which is assumed as there is no bond written, CH2Cl. All right, plugging in actual values into my equation now. I'm going to switch colors so we don't get super confused. On my reactant side, I would have, oh, sorry. I'm going to reiterate this section actually. I'm going to bring it back down. Oops. Just scooch all this around so we can analyze the bonds a little better. All right. So before I plug in my values, I notice I have the same bond on both sides. This is addition and subtraction. There is no fancy anything else going on, so I can actually cancel out four of my CH bonds on my left side with four of my CH bonds on my right side, making this times one. So I can actually do this much more simply by just incorporating my HCl, which is going to be 431, and my missing, because you may be screaming at your computer, C double bond C that I did not add before, which is going to be 614 kilojoules per mole. This time I'm not going to be writing all the kilojoules per mole just to save a little time. We will subtract that from the CH bond, which is 414. And we will also subtract 324 from the carbon chlorine bond. We will find our total answer being the energy, or the delta H, that is absorbed, as this is a positive value, is 307 kilojoules mole inverse. So the important thing here is if you have the same one on both sides, you can often just cancel them out to make your work a little bit easier. Anyways, I hope this helps and have a great day.